Hello everyone, my name is Hassan Beyzavi, an assistant professor of chemistry at the University of Arkansas in Fayetteville. Today I would like to shortly talk about one of the aspects of our research, which is focused on the nanomaterials which are porous, known as metal organic frameworks. So basically, talking about porous materials, they are already been designed by nature. As you can see, for example, our lungs, bones, or eggshells, or butterfly wings, they are basically made of porous materials. And also in our daily life, we are using porous materials as well, like human have been able to make this material because they have so many applications like papers, chalk, sponges, and even a yummy cake. They are all basically porous, which means there are some void space in their structure. When it comes to the pore size, we have different definition, basically depending on the diameter of the pore. For example, if the diameter is less than 2 nanometers, we call them micropores. If they are between 2 to 50 nanometers, as shown here, we call them basically mesopores, and if they are beyond that 50 nanometer limit, they are macropores. So basically, the way that we make these hybrid materials to make extended networks using basically molecular structures would be to use a metal system, like in this case is a manganese 2 metal as the inorganic side, as well as an organic linker, which we also call them struts. We basically mix these two together, and in this case we have a linear linker, benzene dicarboxylate, and we would essentially make this cubic structure. This is a cartoon representation of this material, and this is basically a nice actual crystal structure of basically these systems that soon we will go to the TEM and SEM as the electron microscopy lab to have a look at the MOFs that we learned together to synthesize. It's also interesting that these materials are modular, which means we can use different metal centers with different coordination spheres. For example, we can use a tetrahedral based metal with the coordination sphere of, as you can see, it would lead to a tetrahedral structure, or octahedral, like here we have the octahedral structure, and as well as the trigonal bipyramidal, and actually there are more metal coordination spheres. We also can use different organic linkers. This is a linear linker. This basically has benzene tricarboxylate, which looks like a trigonal system. Or besides the carboxylic acid linkers, we even can use nitrogen based, like in this case methyl imidazole. And these actually would be the first one, and the last one would be the two MOFs that we basically learned together how to synthesize them. So MOFs, actually metal organic frameworks, have different features. Like the first and very important one would be that they have a very high surface area, and also they have a large surface to volume ratio. They have a pretty large pores, which enables the guest molecules to go inside these 3D materials, which actually are 3D, and allows the diffusion of the guest molecules like gas molecules or other substrates. Usually they have a high stability so that we can use them in real application in industry and our daily life. The design is very flexible, as you could see that we can change the metal and linker and come up with thousands of new structures, and also they are electrochemically active. Let me talk about the surface area further. This is one of the metal organic frameworks made at Northwestern University, known as NU100, and the surface area of this MOF actually is 7,000 square meter per gram. And just to tell you and show you basically what it means in the actual comparison and analogy, is that basically the one gram of just this metal organic framework has a higher surface area than the entire football field. For example, this is the Razorback Stadium at University of Arkansas in Fayetteville, and the surface area of the field is just 5,400 square meter basically. So this 1 gram of this material has an higher surface area. If we are able to stretch this out, it would basically fully cover the field and would have even extra surface. So basically for today, we are going to synthesize a MOF, which is shown here, known as MOF5, one of the early MOFs which was synthesized. And we are going to use benzene dicarboxylate with zinc oxide as basically the linkers, as the metal nodes to link basically the benzene dicarboxylate and come up with this system, which basically would essentially lead to cubic cool structures that soon we will go to our electron microscopy lab and have a look at it. So now let's go to the lab and learn how we can synthesize them, and further how we can have a look at the structure under the electron microscope.
So today we are going to make MOF5. To make MOF5, we need these chemicals. This is terephthalic acid, which is linker for MOF5, and this is zinc acetate, and this is metal. And also we need base, triethylamine, and we use 2 kinds of solvent. First one is DMF, and the second one is ethanol. I already got a small amount of DMF here, and ethanol also. So we use terephthalic acid, 25 milligram. I already measured. Also zinc acetate, we need 85 milligram. I already measured. So first, we will pour this material inside of this round bottom flask. Terephthalic acid. I will add DMF 1400 microliter by using micropipette. Seven hundred microliter. Next, we will add 600 microliter ethanol. For last, we will add triethylamine. (42 microliter). That's all we need to use for MOF5 synthesis. So now we will start at 300 RPM. This is starting now. So it takes 2.5 hours to make MOF5. This is MOF5 after 2.5 hours. Now you can see the crystal of MOF5. So we can do centrifugation to collect this MOF5. After centrifugation, all moth is at bottom. And we can pour to get rid of this solvent, and we can dry moth. Now we are going to prepare grit. This is grit holder. As you can see, there are a lot of grit in this holder. So I will get one from here. Later we will see samples on this grid. Then this is moth 5. I will drop very tiny amount of moth on this grid. I will dilute first. Inside of a pipette. Maybe this amount. We will drop our sample here.
There we go.
This is a transmission electron microscope. It's a JEOL GEM 1011 electron microscope. It's a transmission electron microscope, meaning that the beam transmits all the way through the sample. And the picture you get from that will be a two-dimensional picture, and that will be different than the three-dimensional picture that we'll get with a scanning electron microscope. So this microscope has a resolving power of 0.2 to 0.4 nanometers, and it has an accelerated voltage of 100 kilovolts. So that means that there is 100 kilovolts that will be coming down from the top, going through the whole microscope and into the sample. So we have this will be where you will initially see the electron beam, and then that we will switch the camera over to here, to the monitor, and the picture will end up on the monitor. You can take that picture, and that will go on a flash drive, and it can be presented for an article or for anything else that you need. And you see now that the microscope, they have a lot of lenses and things. The lenses, you have a condenser lens, an objective lens, and a projector lens. And the condenser lens is for the light source, the projector lens is the focus, and the objective lens is for something else. So those are the three lenses. Just like you have with the light microscope, you have objective lenses and condenser lenses. And you can see the different processes here. We have different airlocks and valves and stuff that need to be opened and closed in order for the microscope to begin. And we look at these three vacuum systems here to be sure they are in the correct position before we're able to use the microscope. And so that's basically the start of the transmission electron microscope. And Yoshie is going to take over and show you how to put the sample in the microscope and how to focus it and end up with a very nice electron micrograph here on the monitor.
Well, now we are going to prepare a sample. This is a sample folder.
So you have
So is the sample in there yet or not?
We are going to put in a sample here.
Okay.
So can you make it closer? So
Yeah.
there are two holes.
Uh-huh.
So we are going to put grid in it. So grid is now here. So we are
Okay.
going to see these samples. on this grid we have very tiny nanoparticles.
Okay.
Okay, so let me prepare the sample. Okay.
So these little circles that I see, that's the sample?
Yes, this is grid, and the sample is on this grid.
Oh, okay.
Okay, so sample is very, very tiny, so that's why we have to use this machine.
Mm-hmm.
So first we will check MOF5. So this sample folder has two places to put grid. So we can see left one first and right one is second. So I'll
Okay.
put two kinds of grid.
Have to be very precise.
Yes.
Okay.
So I will close this folder. Now we are going to put this sample powder in this machine. So here we are going to put this sample powder.
Yeah.
This is first time the green light turned on. So after the third light turned off, we will put this sample powder perfectly inside.
Mm.
Then slowly, gently turn and just they go inside
Okay.
by themselves. So bump a little bit. Okay. So now sample is inside, we can see something. Light is turned on now.
Okay.
This is clean. Is it okay to turn off?
So that is the grid that was super tiny that we saw over there.
Morphs.
Mm-hmm.
This morph is mid 101. I'm trying to find beautiful shape from now.
Whoa. That is amazing.
This is a hexagonal
Yeah.
shape, and this morph is G8.
Looking like a honeycomb.
Mm-hmm.
Here are basically showing about the different possibilities that we can design different organic linkers with different geometry, as well as different metal ions or clusters, and basically put together and come up with thousands of structures using this modular approach. And let me show you several examples here. For example, this is a linker, benzene dicarboxylate, which in the presence of copper or zinc could lead to this structure known as HCOS. In this case, we can make actually MOFs out of the aluminum or iron using the linear linker, or we can use an imidazole-based system using zinc and manganese and come up with metal organic framework. This is another representation showing the yellow sphere that depicts basically the empty space in these materials, so that the gas molecule could basically diffuse into the pores like a gas molecule. And this is one of the examples of the metal organic frameworks that basically was prepared, and you can see that we can have a large actually hexagonal and trigonal channels, and it has several features like a high surface area, very high basically stability, and as well as the presence of the high density of the metal cluster, which in this case is hafnium. So let's have a look in depth in this material. So you can see that we have two types of channels. One channel is hexagonal and the other one is trigonal. Here we have a diameter of about 30 angstrom or 3 nanometers of this hexagon, and you can see that when we look at different angles, we can see that we have linkers and we have the metal cluster, which are basically stitched together. Here is another view that you can see even from this angle, this material is porous, showing the linkers and the metals which are actually connected together. And here is a deeper look at the metal cluster, which is actually based on the hafnium. So there are 6 metal centers which are connected and bridged by oxygens, and they are connecting the linkers as well.
The scanning electron microscope, the transmission electron microscope, when the electron beam comes down, when the electrons come down, it goes through the sample, and it gets a 2-dimensional image. But on the scanning electron microscope, the beam comes down and there's a scanning over the sample, and you get a 3-dimensional image rather than just a 2-dimensional image.
Okay.
And so that would be like if you had people like to see bugs and things of that sort. The scanning electron microscope is real popular for that kind of looking at insects. And the resolution on the transmission microscope, we had 100 kV. On the scanning microscope, we may have 15 kV to 30. So the resolution is a lot less. It's 1 nanometer compared to 0.2 to 0.4 nanometers. And so it's a little bit different microscope to that. And so basically you still have an electron source at the top, and you have electromagnetic lenses that actually focus the electron beam. So instead of having lenses, glass lenses like with a light microscope, we have electromagnetic lenses that focus the electrons, and that can pull them one way or another and get them to focus on the sample. There's different detectors on here. The detector, this is for the secondary electron detector. So what happens here, the electrons come down and they bounce off. So they're secondary electrons rather than the primary electrons that come down on the other microscope.
Which is why you get the 3-dimensional
Right, you get the
image.
3-dimensional because, and that's a little detector for those secondary electrons. And we have other fancy pieces of equipment here for other things. But yeah, that's our samples right there. And what we have to do is to raise it up after it, all the green's on there. We have to have a certain perfect working distance for this aperture and the electrons to be at the optimum height. So.
Whoa.
That cubes in the left corner. Zoom in.
What about this one? Or
Maybe.
this is also isolated. Yes.
Wow.
MOFs have found actually a growing number of applications, including in catalysis, gas storage, chemical sensing, gas separation, drug delivery, and biomedical imaging. Therefore, these materials are pretty interesting to further explore and learn about their exciting synthesis, how we can make it. That today we will learn it together, and also we'll apply them as well. So here is the drug delivery application that I'm showing, that a drug molecule can be encapsulated inside these pores in these materials, And we also can have biocompatible metal organic frameworks that actually can be injected to human, and then they slowly can first target the wherever we want to bind them, for example a tumor cell, and then slowly release the drug, which would be anti-cancer. The other application that I already mentioned would be gas storage, because gas molecules like to be absorbed on the surface, and since these materials, as mentioned, they have a high surface area, therefore they can have a very high uptake of the gas molecules as the gas. And the other application would be to use them as catalysts, like the enzyme mimetics, because the linkers can be catalytically active and the pores can actually mimic the enzyme's pocket.
So now we are trying to do application by using MOF5 that we made. This is iodine solution, iodine in methanol. So radioactive iodine is bad for human being. So if we can encapsulate iodine by using MOF is very good. So this is curcumin. MOF is also used for drug delivery system because MOF has huge pore, so we can encapsulate drug inside of MOF. This curcumin is not drug, and I got this yellow curcumin from spice, turmeric spice, which is common spice at kitchen, so you can use your spice for your experiment. So now I'm going to add MOF that we made. This time we'll make sure to add a lot of MOFs. When curcumin and iodine are encapsulated by MOF, this solvent will become clean. This is standard iodine before we added MOF5, and this is after MOF5. After we added MOF5, and this is curcumin standard without MOF, and this is curcumin with MOF. You can see color change, and if you can see the MOF5 under this inside of curcumin bottle, you can see yellow MOF5. So MOF5's color also changed from white to yellow.